Okay, let's talk about something we use literally every single day, but probably don't think much about. Batteries. These little powerhouses run our entire world. But how do they actually work? Well, today we're going to tear one open, figuratively, of course, and find out.
I mean, you've got to admit, it feels a little like magic, right? You pop a tiny cylinder into your remote and boom, it just works. You plug your phone into a wall and it somehow stores up hours of energy in a little black box. What is going on in there?
Well, the secret isn't a magic spell or anything like that. It's chemistry. And it's actually a really elegant, really cool chemical reaction. Once you get the basic idea, it all makes perfect sense. So at its most basic level, all a battery is an energy converter. That's it. It's got all this potential energy stored up in its chemical ingredients, and when we need it, it cleverly transforms that chemical energy into electrical energy. And that's just a fancy way of saying it gets a bunch of tiny little particles called electrons to start moving. Now, to really understand the story of how a battery works, we first need to meet the cast of characters. And you'll find these three main players in pretty much every battery, whether it's a tiny watch battery or a massive one for an electric car. First up, we have the anode. This is the negative end of the battery, our starting line. Think of it as the component that is just dying to give away electrons. It's super generous, and this generosity is what kicks the whole process off. And on the other side, we have the cathode. This is the positive end. And if the anode is the starting line, well, the cathode is the finish line. It is chemically designed to attract and welcome all those electrons that the anode is so eager to send away. And finally, we have the real unsung hero of the whole operation, the electrolyte. This is a special chemical paste or gel that sits right between the anode and the cathode, and it acts like a very strict bouncer at a club. It says to the electrons, nope, you can't pass through me. But it does let other charged particles, called ions, move back and forth. And that little detail is absolutely crucial. All right, so we've met our characters. We have the giver, the taker, and the gatekeeper. Now let's see what happens when we put them all together. This is the main event. This is the chemical dance that generates power. Now, the fancy science name for this dance is a redox reaction. Sounds complicated, I know, but just break it down. It's two things happening at the same time. You've got oxidation happening at the anode, that's just losing electrons, and you've got reduction happening at the cathode, that's gaining them. One side gives, the other side takes. That's the whole game. So let's walk through it. Step one, you flip a switch on, say, a flashlight. You've just created a path, a circuit. Instantly, the anode starts giving away its electrons. But remember, the electrolyte bouncer won't let them cut through the middle of the battery. So what do? They're forced to take the long way around, traveling outside the battery, through the flashlight's wiring, powering that little light bulb on their way. They race all the way over to the cathode, which is waiting to accept them. And while all that's happening on the outside, those little ions are shuttling through the electrolyte on the inside to keep everything chemically balanced. That constant flow of electrons through the outside circuit, yep, that's electricity. Now that whole process perfectly explains your typical disposable battery. But what about the ones in our phones, our laptops, our cars? The rechargeable ones. How do they work? Well, guess what? The lithium-ion batteries that power pretty much everything these days work on the exact same principle, the same dance. But they have this one amazing trick up their sleeve. Their chemical reaction isn't a one-way street. It can actually go in reverse. So here's the difference. A primary battery, like your standard AA, has a one-and-done reaction. Once the chemicals are all used up, that's it, game over. But a secondary or rechargeable battery is different. When you plug your phone in to charge it, you're basically using electricity from the wall to force all those electrons to travel backwards, from the cathode all the way back to the anode, resetting the whole system so it's ready to go again. Okay, so we know electrons are flowing, but what's actually making them move in the first place? Why do they want to travel from the anode to the cathode so badly? Well, that's where something called voltage comes in. And probably the easiest way to think about voltage is as electrical pressure. It's the force that's pushing the electrons through the wire. And that pressure can be wildly different depending on the battery. A little AA battery gives a pretty gentle push, about 1.5 volts. A car battery needs a lot more oomph to crank an engine, so it's putting out 12 volts. But an electric car, to move that whole machine, it needs a massive amount of electrical pressure, often around 400 volts or even more. The more volts, the stronger the push. But here's the thing.
Whether it's a single-use battery or one you can recharge 1,000 times, every single battery eventually dies. So why can't they just go on forever?
Well, it all comes back to that chemical reaction. Over time, the materials just wear out. The anode literally runs out of available electrons to give, or the cathode gets so full it just can't accept anymore. Even in rechargeable batteries, a little bit of the material gets degraded with every cycle. Eventually, the reaction just stops. It's really no different than a car running out of gas. The battery has simply run out of its chemical fuel.
So there you have it. A simple, elegant chemical dance happening inside a tiny metal can is what powers almost every aspect of our modern lives. It's pretty amazing when you think about it. And it really makes you wonder, if this incredible chemistry is what's powering our present, what kind of new discoveries will power our future?